Okay, so we're gonna go ahead and get started, I should say. So I don't know why the first slide kind of cut off like that, but this is for the final review for 2310. I'm Megan.
I'm Kawan.
And then Varsha couldn't join us today, so we're kind of taking over her part. So we're gonna get started now. So part one, we're gonna work on register files and processor design. Unfortunately, I couldn't put a full MIPS code in. So what I would recommend is Zybooks is a really great opportunity for that. But whenever you do Zybooks with the MIPS coding, run it through line by line and really pay attention to how like the data memory and register file values change with each line. But I feel like after we go through register files and processor design, you'll kind of get a better sense of your MIPS code as well, because you have to understand what the MIPS instruction itself is actually wanting to do in order to get all that done. So let's get started. This is just like a basic overview. You should have something like this, I believe, for your test. You'll probably only have this left portion here. This is just something that we added on, kind of like what each instruction looks like generally, in which all the ones with a number sign in front are all the registers. And then if these are a constant, just a little notation. But I believe for your test, you'll only have this left side. So we're gonna start off with register files. Register files you'll need to know for the processing as well. Sorry, I forgot to pull something out. Okay. So first things first, whenever you do these instructions, I really want you to think about what a MIPS instruction is actually doing, like before we even get into any of this work. So what does a load word do in general is what I want you to think about. So what I like to think is I like to say, okay, load word likes to load data from data memory into a register. And it's really important that you know, like, is it taking from data memory or is it taking from a register? And where is it storing that value into? Because store word would be the opposite, right? And this is really important. So let's work through this register file itself. Anytime you see these parentheses, this automatically should tell you data memory address. In MIPS instructions, you won't have parentheses for anything else. It always refers to a data memory address. So what it means is we want to find what is stored in register T6. So whatever the contents of register T6 are, and whatever this constant in front is, we're going to add it. So that means our data memory address is going to be equal to whatever's, this is notation for contents of, but whatever's in register T6. And then we're going to add that constant 8 to it. And that's the data memory address we're going to access. Okay. So, and then what the load word does is this register over here, we said it's going to load data from the data memory address. So whatever's in this data memory address, we're going to store into this register. And it's really important that you know that kind of relationship and how that you can explain it in basic terms before you actually go through the register file itself. So based off of what we said so far, now we have to figure out what we're reading from and what we're writing to. So we said that we're going to store into register T4, which means that we have to write into register T4. So that means here in this write decoder, this is what we're going to be working with T4. Okay. In order to get the data memory address, we had to read what was in T6 in order to add the 8 and then to go to that data memory address to get the value, to get the data. So we have to read from T6. So that's going to be in our read decoder. And then we aren't working with 3 registers. So this last decoder is, we don't care about it. We don't care what's in it. So we can go ahead and say this enable here has to go to 0 because we're not going to use it. And then we don't care what goes into any of the other values because we're not going to use it anyways. Okay, starting with, let's say, the write decoder, we said that we're going, or actually, let's start from reading because the first step in a load word is we're going to read from T6 and then use that to go to data memory. So let's start with the T6 reading. So if we're gonna read from T6, then this address has to be 6 in 3-bit binary. So 6 in 3-bit binary is 110. And that means that D6 is going to be on and everything else is off because it is 1 hot. And I almost forgot that you have to also do your enable. So your enable will be a 1 because we're using it. Now I have register contents on the left here just to give us some actual values. So we're reading from T6. So I'm going to go to T6 and I see that T6 is holding a 280 in decimal. So that's the data that's going to come out. Oops. Now we're going to be writing to T4. So we set that enable to 1. And for T4, we have to write T4 in 3-bit binary. So that's 100. And that means that D4 will turn on and everything else will be off. Now for this, we have to do a bit more steps. So the data that's going to be written into here isn't, we can't just find it from these register contents. And I didn't write down the data memory address, but we'll get to that in a bit. But just from these contents. So we have to think again, what does a load word do? So a load word, we said, goes to the data memory address that is the contents of T6 plus 8. So let's get that data memory address. This data memory address, T6 was 280, we said. So 280 plus 8. So we get 288, which means the data memory address that we're going to be accessing is data memory 288. And I forgot to write on these slides, but let's say that the contents of data memory 288 is equal to 243, for example, just a number. So we go to that data memory address and we said that we want to take the contents of that data memory and put it into the register T4. So 243 is what's going to be stored into register T4. So we had to go to the data memory first in order to figure out what's going to be stored. Moving on, store word is the opposite. So you want to think something along the lines of store data into data memory from a register. So before we said we were loading from a register and we're storing loading from a data memory and we're storing into a register. This time we're going to store into a register from, sorry, I keep messing up my words, into a data memory from register. My bad for that. So similar process, anytime you see a parentheses, you're going to think data memory address. This is always going to give you a data memory address. So in order to get that data memory address, we have to read from this T7 so that we can add the constant in front to it. And now in this case, we have to figure out what are we doing with T5, register T5. We said that we're storing data into data memory. So we're writing to data memory, but we're getting that data from a register. And that register is T5. So we're actually wanting to also read from T5. You'll notice that we said that we had to write into data memory, but then here we said we are not writing at all. That's because we're only working with the register file right now. When you get to processor design, that's when you actually see the data memory block somewhere else, and then you'll be writing into that. So that's important to note here. So that means that we aren't using the write decoder at all. So we'll set that enable to 0, and everything in it, we don't care what the value is because we are not using it anyways. So now we have to figure out, we have two different read decoders and we have two different registers we have to read from. You might be wondering, does it matter which one I read from where? Like, can I read from either T5 or T7 here? Or is there a specific order that you have to do it in? The answer is yes, there's a specific order, and it's easier to see whenever you actually do the processor design. A little trick though, if we looked back here, T6, the one that we read from to get data memory address, was in this second, or this first, I should say, this first read decoder. That same thing is going to happen over here. So actually over here, this will be for T7, and this will be for T5. And the reason for that is just the way things are wired, typically. So if you ever forget, you can just go back to load word and take a peek and see, and remember that this is your register that you use to go to data memory. This is where you read it from. So it's a little bit counterintuitive because you might say T5 would go there just based off of looking on the instruction alone. So for the address, we want it to be 3-bit binary. So 7 and 3-bit binary is 111. That means D7 will turn on, everything off. We are using this decoder, so we want to set enable to 1. And then what comes out is the contents of T7, which based off of the register contents on the left, I got that that's 640. And then now let's do the second read decoder. T5, we want the enable to be on because we're using this decoder. 5 in 3-bit binary is 101. That means D5 will turn on, everything off. And we look at the contents of T5, and I get on the left that the contents is 894. So that's for a store word. So now ADDIE. Similar to before, we want to figure out first how this instruction actually works in basic terms before we start going into the, the device itself. So in an ADDIE, we have this register, I should say, this middle register here. And what we're going to do in an ADDIE is we are going to get the contents of T6, and we are going to add this constant over here to it, and then store it into T4. So if I write that as like a little equation, I'm just going to say the contents of T6 minus 17 is basically going to be stored into T4. That's what this line is doing. Okay, so then we have to think, which ones are we reading from, which ones are we writing from? So then we look at T4, and looking at this instruction that we said earlier, this equation, we're going to be storing the sum into T4, which means we're going to be writing to T4. For T6, we're going to be reading from T6 because we want to find the contents in order to add it to the constant. And so then we don't use the constant, we don't have to read from the constant or anything like that. So we don't have to use a decoder for that. So we have the right decoder for T4. So let's use the T4. Setting enable to 1. The address is 3-bit binary for 4, which is 100. D4 will turn on, everything off. And right now we don't know what's written in it, so we'll hold off on that. Moving on, T6, set the enable to 1. 3-bit binary for T6 is that. And so then D6 will turn on, everything else off. And what comes out is the contents of T6, which I had was 280. So now going back to the right decoder, we said that what we're going to write into register T4 is the contents of T6, which is 280 minus 17, which will be 263. So that is what's going to be written into T4. And then this last read decoder, we don't care about it, we don't need it. So set the enable to 0, and then everything else do not care. Make sure you actually set the enable to 0, because this enable is not a do not care. Because if you put it as a 1 instead, then it's saying that you're actually going to use all of these values, which we don't want to happen. So make sure to set that enable to 0 when you're not using it. Add is really similar to ADDIE. Basically, instead of having a constant over here, you'll notice we have a register. But similar principle where we say, oh, T4 is going to be equal to the addition of the other registers. Which means for T4, we're once again still writing into this first register. But now we have 2 registers to read from because we got to add whatever is stored in them. Okay, so we have that T4 should be in this writing. Set the enable to 1. 3-bit binary for 4 is 100. That means D4 turns on. Everything else off. And at the moment, we don't know what to store in it because we haven't read from either T3 or T6, and we haven't added them together. So we're going to hold off. Over here, for this one, it's kind of intuitive. So we have 2 to read from. You kind of just do it in order. You have T3 and T6. So it's not like the store word where it's opposite. This one is the order it comes in is the order that you put it in. So turn the enable on. We have for all of them. For this middle decoder, we have 3-bit binary for T3, so that's 0, 1, 1. That means D3 will turn on, everything else off. And what comes out is the contents of T3, which is 15. And then T6, 3-bit binary is 1, 1, 0. That means D6 will turn on. And what comes out is the contents of T6, which is, oops, I keep doing that, 280. Okay, so now we go back to what to store into this T4, the write decoder. And we said T4 is equal to the contents of T3 plus the contents of T6. So that will be 15 plus 280, which is 295. So that is what is going to be written in. Moving on, I just kind of did this for all the different instructions just to get more practice in. But next we have the subtractor. Also, this is basically the same thing as the addition. The only difference is that instead of adding the values, you're going to be subtracting them. But the same way you go through the register file. So we have that T5 is going to be equal to T4 minus, in this case, T1, which means that we're going to write to T5, and we're going to read to T4 and T1. So here we have T5, set the enable to 1. 5 and 3-bit binary is 101. Means D5 is going to turn on. And then we don't yet know what we're going to write in. So we move on to the first read, which is T4. Set that enable on. 4 and 3-bit binary is 100. So that means D4 is going to turn on. And what comes out of T4 is the contents of T4, which is 91. This one will be T1, enable to 1. 1 and 3-bit binary is 001. So that means D1 is going to turn on. And what comes out is the contents of T1, which is 42. So now we move back to the write decoder. And we said that what we're going to write into it is the contents of T4 minus T1. So that means we're going to do 91 minus 42, which if you do that, you get 49. So that's what's going to be written in. Very similar process as the add instruction. So now we get into something a little bit different, which is the set less than. So for this one, you also have to know how to explain it in basic terms. So As usual, this is what we're going to write our result into. And then here, what a set less than does is it compares the data in these two registers. So it's going to get the contents of T2, it's going to get the contents of T3, and it's going to say, okay, what is the relationship between them? Is it, or I should better say, is it less than? Is register T2 less than register T3? So if it is less than, so this statement is true, then it's going to write a 1 into T0. If it's not, then it's going to write a 0. So I'll write that down here. So if T2 is less than T3, then I'm going to put into T0 a 1, essentially saying, yes, this statement is true. If T2 is instead greater than T3, then I'm going to write into T0 a 0, basically saying that it's not less than. Okay. So once again, T0 we said is where we're going to write our results. So that's in our write decoder. Set the enable to 1. 0 and 3-bit binary is 0, 0, 0. So D0 will turn on and everything else will turn on. And then we don't yet know what we're going to write in yet because we have to compare T2 and T3 first. So first, read decoder. We're going to read from T2 and set that enable on. T2 will be 0, 1, 0. And then D2 will turn on. Everything else will be off. What comes out of T2 is 8795. And then we move on to the second read decoder. Set the enable on. This one will be for T3. 3 and 3-bit binary is 0, 1, 1. D3 will turn on. Everything else is off. And the contents of T3 were 15. So now we have to do a comparison. We have to say, okay, well, is T2 less than T3? So we have 879 or 8,795, sorry, 15. So is that less than? No, it's not. So what's going to be written into T0 is a 0. That kind of changed the curriculum up. So if this is something that you guys have never seen before, please do let me know. It has been like a long time, like 2 years since I've taken this class. So yeah, just let me know if like you see something you're like, we don't have to learn that, and I will just move on. So for this one, we have a branch if equals. Oops, did not mean to hit that. So basically, BEQ stands for branch if equal. So what it's going to do is it's going to look at these two register values, T7 and T1, and it's going to say, okay, if they're equal, then we are going to branch. If T7 is not equal, or the contents of T7 is not equal to the contents of T1, then we're just going to ignore the statement. We're not going to do anything. For this register file itself, this doesn't really mean much to us. It's mainly in processor design, which I think they took off for you guys, if I remember correctly. But what's important to note here is that we're doing a comparison of the two registers, which means we have to read from both registers. And that is all we really do with the register file with this instruction. So we're not going to be writing to any register. So our write decoder has an enable of 0. And then everything else, we don't care what is in it because we're not going to use it. And then for reading it, we have T7, set that enable to 1. 7 and 3-bit binary is 111. That means D7 is going to turn on. Everything else will be off. And what comes out is the contents of T7, which in this case is 640. Next, we got to read from T1 in order to do the comparison. So set that enable to 1. 1 and 3-bit binary is 001. D1 will turn on, and then everything else will be off. So the contents of T1 were 42. And in this case, this is all you have to do for the register file. Branch not equals is same process, but essentially the opposite result, right? So we say, in general, branch if it's not equal. So that means in this case, if T5 is equal to T7, then this time we'll ignore. And then if T5 is not equal to T7, then we're going to branch. So in this case, same as the last one, we have to read from both in order to compare them, which means we aren't writing to any register. Set the write decoder enable to 0. Everything else we don't care about. And then for the first read encoder, we'll go to T5, set the enable to 1. 5 and 3-bit binary is 101. D5 will turn on. Everything else will be off. The contents of T5 are 894. And then the last read decoder, we will do T7. Set the enable on. And then 3-bit binary is 111. And D7 will turn on, and everything else will be off. And so then what comes out is the contents of T7, which is 640. So that's it for the register files. I'm going to go through all the instructions for the processor diagrams, because I'm pretty sure how they do it is in the test you'll get like 1 to work on. It will be a random 1. So it's important you know these. I will say that for today, I will not be working on converting to machine code, machine code, the binary equivalent of these instructions. I'm kind of just going to give it in this one. If you do need help on that, though, I do go more in depth on that one in the previous exam review from last year. It'll be on the IEEE YouTube as well. So just search that up if you need help on actually converting to machine code, because there I go through, I believe, every single type of instruction. But for today, we will not be doing that. I will just be giving it. Oh my God, I keep clicking that. So the machine code for a load word is 1000, for this load word, I should say, where this is T7. This is T0, and then I believe I did the right amount. Oh, God. This one, okay. And this is the immediate, that's 4. And this is the RT. This is RS. So let's say you've done the machine code conversion already. You got this line of binary numbers, and now you have this processor design in front of you. First things first, there's little freebies, all these green ones here that say IR and then like a number, another number. Those are just telling you straight up like the placeholders. So for example, this bit right here is 31, and then it goes 30, and then 29, 28, all the way down to 0 over here. So in this first blank here, it's basically telling you to put in the first 6 numbers, which are these. So we'll put in 1 0 0 0 1 1. And this one right here is telling you to put in the next 6 or 5 numbers, which is there, which is the same thing as T7. And then we're just going to keep doing that until all the bits have been used. This is the same thing as T0. And down here, this is it's asking for the next 5 bits. 2, 3, 4, 5. You'll notice that they're all zeros, which is kind of funky. It's just because in this instruction itself, we don't really care about that. In another instruction, that will actually be a useful number. And then down here is the last 16 bits, which are just all of these. I don't feel like writing all of them, so I'm just going to do a bunch of dots and then 1 0 0. But basically, you'd copy this whole thing in. Okay, so now we have to think about what a load word does. This is where it's really important to be able to explain this in really simple terms. So we said, what does a load word do? Okay, it loads from data memory into a register. Okay, which means we're writing to a register, this one, we're reading from this one, and then as a whole, we're reading from data memory itself, right? So we have a bunch of, we could start in multiple places. You could honestly start anywhere and kind of just work around. I'm gonna start maybe at the register block just to make things a little bit simple. So right here, we have this write address and we have this mux controlling what goes into it, right? So we have to decide with this mux select what we want to pass. So in this mux, we have either the option of T0 up here, or we have an option of just a bunch of zeros. So we said that we want to write to T0. So we want that T0, this one right here, this number, to pass through. So we are going to select this mux so that it selects this 1 up here. So this mux selector, I'm putting it as A1. That means that 0 1 0 0 0 goes through, which is the same thing as 2 0. Sorry, I'm looking in the wrong place. So that makes sense. Okay. I'm going to save what we're writing in for later because we have to read from data memory for that. And instead, we're going to move on to this right side of the register block. Read data 1 will just read whatever is connected to address 1, which is T7, right? So what comes out of that is just the contents of T7, which is 20. So this is the same thing as the contents of T7. And that's just because that's connected, hardwired in. So then we come to this ALU, and now we have to think, okay, well, is there any like arithmetic that we have to do in this case? In this case, yes. And what we have to do is we have to get the contents of T7, and we have to add this constant 4 to it, right? Because we want to get the data memory address. So what we want to come into this bottom part is the constant 4. Because up here, we already have the contents of T7. So down here, we want it to select 4. We have this mux. This mux is connected to either read data 2 through the 1, or through the 0, it is connected to down here with this sign extend. So this sign extend is basically just our immediate, right? We have our immediate here, which is the number 4. So we want this bottom path to pass through. So we want this mux select to be at a 0. That way, I'm just gonna write 4 in binary. Okay. That way that 4 goes through. Okay. And also I forgot to write down here actually. My bad. But this is the last 6 bits. So it's 0 0 1 0 0 0. So what will go through here is 0, 0, 0, 1, 0, 0, which is the same thing as 4, right? So this ALU, we said that we wanted to add, so the operation will be adding. And what comes out is the contents of T7 plus 4, which in this case will just be 24, essentially. So now this 24 is connected to two different places. One, it's straight up connected to this data memory address, so we can write that in. And then second, it also has a line that goes down here to that mux. Okay, so eventually we're gonna have to make a decision over here whether we want to use it with that mux or not. So now we have to think about what we're doing with data memory. So we said that a load word loads from data memory, so we're gonna take a value from data memory, and then we're gonna put it into a register. And we said that this right here was our data memory address that we calculated, right? Because we said to get that data memory address, you had to read from T7 and add 4. So this is exactly data memory address, which is why it's there. And we said that we want to read from it. So data memory, we're going to set the read enable to 1 because we want to read from it. And that's going to allow this to go through and get the contents. So the contents of data memory, and then just pretend that was a 24, by the way. From data memory 24 was 289. So that's when it's going to go through. Are we writing to data memory at all? In this case, no. So you have to set the data memory write enable to 0, which means that we don't care what goes in there because we're not writing to it anyways. Okay. So then we have to figure out what comes out of this data memory block through this mux. This mux has two options. It either has this value here, the 289, or it has this line that goes all the way to the 24. So let's look at where this connects to. If you follow this path all the way, it connects all the way to this write data. So whatever we choose with this mux is going to be written into a register. So we said that we wanted the contents of that data memory, so that's what we're going to put through by putting the select as 1. That way that 289 goes through and goes all the way into the write data. And then we're missing a few here that I forgot to write. Right here, this register file write enable. Are we writing to register file in this case? Yes. Yes, we are. So we want to set that enable to 1. And then right here, this read data. In this instruction itself, we don't really have to read from a second register. So in this case, we don't care what is in it. But also, since this is hardwired in and we're connecting this T0 to it, technically what's in there is a 16. But if you put an X, it would also be correct because we don't care what's in it. We're not using it anyway. So either way for that one is correct. Any questions so far? Okay. So next we have the store word. For store word, we say the opposite. We want to save into data memory from a register. I'm going to go ahead and give the machine code again. Remember, you can always look back at the previous video for more in-depth on that. So this is the same as T7, same as T1, and then this is the same thing as the 24. Once again, we can just put in the little freebie sections. The first 6 bits go here, and then the next 5, and then the next 5. Wait, I missed it. I missed the first part. I missed the opcode. I thought that looked weird. Okay, there we go. And then this is a bunch of zeros in front of the 0, and then the last 6 bits here. So those are all the freebies. So now, once again, we can start anywhere. Maybe let's start at the register block. We have to figure out what we're doing with these registers itself. So in a store word, we said that we always read from this register because we need it in order to find what data memory address we're going to work with. And then since we're saving into data memory and reading from the register to put into data memory, this is also a read. Which means we're not writing to this register block at all. I can go ahead and set the register file write enable to 0. And then we said we're reading. So here, register the register file. Let me write the. There you go. T1 is connected to the first address. So then what comes out of read data 1 is just the contents of T7. So the contents of T7 are 20. And then here, T1 is connected to the second address. So then what comes out of read data 2 is just the contents of T1, which is a 95. And now we once again get to this ALU and we have to figure out, well, what are we trying to do in this instruction? The only way that we are doing some arithmetic, in this case addition, is once again to find that data memory address, which means that we want to add the contents of T7 with the 24 in order to get that data memory address. So this ALU, we want it to get the 24, which is this bottom path. So we're going to set that select to 0. So that what comes through is the 0, 1, 1, 0, 0, 0, which is also the 24. Right. So then this ALU, we want the operation to be addition. So it's add. And what comes out of the ALU is 20 plus 24, which is 44. Okay. So that is the data memory address. So now we're at the data memory block, and we need to figure out, once again, what we were doing with data memory. We said we're writing to data memory. So data memory write enable is a 1. We're not reading from data memory at all. So data memory read enable is a 0. Okay. So we're writing into it the contents of T1. So if you look here at this, the write data into the data memory, and you follow that path back, you'll notice that it is connected to read data 2, which is the contents of T1. So that is 95. That just goes all the way through. And then we said that we're not reading from it. So right here, that we don't care what goes into it. And as a result, we actually don't care what goes into, or I should say what comes out of this mux as well. Because this mux is connected all the way over here to this writing into the register file. And we said that we don't have to write into the register file in this case. So we actually don't care what comes out of this mux, and we don't care what comes out and goes into this writing of the register files. We also don't care about which register file to write to, because, like I said, we're not writing to any register file. Moving on. Next, we have ADDIE. Once again, I'm going to copy down the machine code. So we said that You'll notice that in this, once we get past load word and save word, we don't really work with the data memory at all anymore. We're only working with register files or constants from now on. So whenever we get to the data memory block later, it'll be a lot of do not cares, a lot of X's. But basically, once again, we're going to put in our values straight up. So opcode, the register T2, just register T3. This is a bunch of zeros, and then that, and then this is the last 6. Yeah. So once again, we have to realize that this is the register that we're writing to, and reading from this, because what this line does is basically saying, okay, store into T3 the contents of T2 plus 10, right? So that means that we are going to write, so we want to set the register file write to 1. What we're going to write, we are going to write to register T3, so that is what we want to go into this write address. So we use the mux to select the T3. So the mux will be a 1. And so what comes through is this. And then we don't know yet what we're going to write into it, so we're holding off on that for now. We're going to read from register T2. That's the one that is in the address 1. So what comes out is the contents of T2, which is a 63. And then we don't read from a second register. So right here, we technically don't care what is in this register data 2. But if you really want to put it in, then it's connected to T3. So the contents of T3 would be going in here, which is 125. Okay. In the ALU, we have to think what we're doing again. Once again, we are adding. So you'd put in an add. We're trying to add the contents of T2 plus the constant 10. So right now we have T2 here. We want the mux to select the constant from this bottom path. So what comes through is the 0, 0, 1, 0, 1, 0, which is the same thing as 10. Whenever we add those, we're going to get 73, because 63 plus 10. And then now we're at this data memory block. So remember, in this instruction, we don't care about the data memory block because we don't use it. So I'm going to set both the write and the read enabled to 0. And I'm going to say that I don't really care what goes in here or what comes out. Which also means that this mux over here, it's a 0. Or, sorry, that's not what it was. This mux over here, we don't care. Actually, wait, we do. Sorry, my bad. Getting ahead of myself. This mux over here is connected to this write data here. So we have to think, okay, what are we writing into a register? In this case, we said that we wanted to write the addition of contents of T2 and 10 into that T3. So we want this mux to select this right here, actually, what comes straight out of the ALU. So in order to do that, the mux has to be selected to a 0 so that that bottom path goes through. So that 73 will go all the way through and into the register file. Add is basically the same thing, except now we're working with 3 registers. I'm going to copy the machine code again. And this is T5. And this is T4. So that is the machine code. We once again put in the freebies, so you get the first 6 bits, get the first. And then the last 6. Yep. So once again, you figure out what add does. You say, okay, well, we're storing into T6 the addition of the 2 registers, right? Which means that we have to write to T6 and we have to read from both T5 and T4. So when we look at the register block, we have this mux to make a decision for. We want to put into the right address T6, which is, oh, I didn't write these. Let me write these real quick. There you go. So you'll notice that in this case, T6 is this bottom path here. So now we have finally something that's not all zeros. So we want this mux select to be a 0 so that that T6 value goes through. Okay. And then we have reading, the first address, the contents of T5 comes out, 44. And then the second one, the contents of T4 comes out, that's 67. We're at this ALU, we have to figure out what it is that we're trying to add. And what we want to add is we want to add the contents of T5 and T4. So this mux should select this top path so that the 67 goes through. And then when those are added, you'll get 111 coming out. Once again, we're at this data memory block. We aren't using data memory in this case, so we don't care what comes in and out of data memory, and we set the enables to 0. We are then met with this mux over here. This mux is connected to that write data, so we have to pick what we want to write into the right address. In this case, we want to write the addition of T5 and T4, so we want to take straight from this ALU. We don't want to go from data memory. So this mux will be selected at 0, and what comes through is this 111, which goes all the way in. And I forgot to write it here, but we are writing, so you want to put that enable as a 1. So we have 2 more of these real quick. Sub is essentially the same thing as the add instruction, except we're subtracting them. So we're saying, in this case, T3 is equal to T0 minus T1. The machine code is, and remember, please go back to the previous review if you need help with converting to machine code. And one moment. Lost my place. Okay. I'm done. So this one's the same thing as T0. This one's the same thing as T1 and T3. So once again, we put in the freebies. This is the same thing as T0. Same thing as T1. And then down here, same thing as T3. This is a bunch of zeros and then 1, 0, 0, 0, 0. And here is the 1, 0, 0, 0, 1, 0. So in this case, once again, we are writing to T3. And we are reading from these two because we have to subtract them. So we want this right address to select the T3 line, which once again, the T3 line is on the bottom of the mux. So that mux select will have to be a 0, so that goes through. Once again, reading, this address is connected to the first read address 1. What comes out is the data of T0, which is 16. And then down here, it's reading from T1. What comes out is a 95. Once again, we get to this ALU and we have to make a decision on what we're doing. In this case, we're doing a subtract, not an add. And we want it to subtract T1 from T0. So right now we have T0 right here. We want this mux to select the data of T1. So we want this mux to be a 1 so that this 95 passes through. 16 minus 95, you will get negative 79. Once again, we're at this data memory address, or this data memory block, and we aren't using data memory. So we don't care about anything in it. And we set all enables to 0 because we're not using it at all. Once again, we're at this mux all the way to the right. We have to figure out what we want to connect into the right data of the register block. What we're trying to put into there is the subtraction of T0 and T1. So we want this negative 79 to go through, which means this mux select should be a 0. And so then the negative 79 will go all the way through. And we're writing to the register block, so that enables a 1. And last one is the set less than. So for this one, I'm going to copy down the machine code real quick. So this is the same thing as the T2. This is the T1, and that's the T5. So in this case, we said that we're basically going to see, is T2 less than T1? If that is true, then T5 will have a 1 in it. If that is false, then T5 will have a 0 in it, written into it. So I'm going to go ahead and put in the machine code. Do the same thing as T2. And so once again, we say, are we writing, reading? What are we doing with the register files? In this case, we said that we're writing to T5, either a 0 or 1. And then in order to compare the contents of T2 and T1, we have to read from both. Right? So this right address here in this register block, we need T5 to be connected to it. Once again, T5 is this bottom path, which means that we want this mux to be a 0 so that that T5 value goes through. This read address 1 is connected to this read data 1. So what comes out is the contents of T2, which is 63. And here what comes out is the contents of T1, which is 95. And let's go ahead and set the write enable to 1 for this register block because we are writing to it. So now we hit this ALU, and what do we want the ALU to do? Well, we want the ALU to compare in this case. So this will do like a set less than or just a comparison in general. Okay. And what do we want it to compare? We want it to compare the contents of T2 and the contents of T1. So right now we have T2 connected to it. We want this mux here to select the T1 path, or the T1 data, I should say, which is right here. So that means that this mux select has to be a 1. So that 95 goes through. So now we have to do this comparison ourselves, but we say, okay, T2 less than T1. In this case, 63 less than 95. Is this true? Yes, it's true, which means what comes out is going to be a 1. Okay. Once again, we don't care about data memory, so we're just going to say do not care, set both enables to 0. And now we're at this mux all the way to the right again, and what we said is we're going to write into T5 either 1 or 0 based on if it's true or false. So once again, what we want to go through is the end of this ALU, which means we want this mux to be selected as 0, and we want that 1 to go all the way in to that register file. Any questions? Kind of went fast. Okay. And we'll move on to part 2.
Hello, so I'm Kawan again, and we'll be going over units 1 and 2, which is pretty much review of what y'all have done. So I have a couple of slides here. I'm not gonna go over all of them because I want to focus more on the problems that we're gonna work on. So yeah, this is the gates that you guys know, the AND gate, OR gate, and NOT gate. Does anyone have questions over these? The NANDs and NORs, XORs, and just want to highlight this thing here, odd parity and even parity, just to make sure whenever you're doing XOR, associate the odd parity with the XOR, and the XNOR you associate it with even parity, because that's a little bit tricky. So yeah, just make sure you guys know that. And here's a picture of converting it to NANDs or NORs. Do you guys have any questions on how to do that? Okay, so let's move on. SOP versus POS. The main thing I want to highlight it's attached to the next slides, but just want to highlight that the format of SOP and POS. And on the next slide, I just associate, and it's also on the slide, associate SOP with min terms and POS as with max terms. And just look at this notation. When you're writing min terms, you use the sigma notation kind of, and the parentheses with your numbers, your min terms and max terms. And for max terms, you usually use the pi symbol. So just a notation thing that I wanted to point out. And the Morgan, we're also gonna work on a problem like that. It's better to show it as an example. I think it's better to understand it, like working an example out. And K-maps, we also have an example of that I would like to work on. So let's get to it. And also prime implicants. If do you guys have any questions about prime implicants? Because I know it could be confusing sometimes. No? Move on. Timing diagrams, these are pretty simple. And you can look at the slides. So let's get to work on the problem. Here's a De Morgan equation, and they want us to apply the De Morgan before simplifying. If we could simplify, which we will after, just to compare our two answers, it'd be easier. But they want us to get the Morgan without simplifying, which makes things a little bit tricky. So let's work on it step by step. So I have my equation here, and it's this one. Let me just write it out here. US plus or S times P naught R plus S P naught R plus Q, and they're all knotted. Okay. So first step that we're gonna do is gonna be the Morgan for OR, and it's gonna be this part over here. So let's apply that. We're gonna keep everything the same, other than the OR that we're applying the Morgan. So I like to split it into two parts just to make things easier. And here's the part where we we applied the Morgan, and everything's gonna stay the same. Notice you gotta keep the inversion signs here to make sure you're gonna do the Morgan for them. And this is called the Morgan for OR. I don't think you have to list that on the test, but just in case you guys want to list it in your work just to be safe. And now we're gonna apply the Morgan for AND. And the way I do it, you could do it multiple ways. You could skip steps, but I like to do it step by step. So we're gonna do the Morgan for AND now, and we're gonna do everything that's outside the parentheses. So the things inside the parentheses, you're just gonna keep the same, and you're gonna put the inverter sign here, and you're gonna apply the Morgan to Q naught and R. It's gonna become P or R naught, or P. I'm sorry. How do you go back to writing? I forgot how to use this. Sorry. To write again. Sorry about that. Thank you. And then so we're back here, and we're applying the Morgan for N here. So it's gonna be P or R naught. And then we're gonna close this parenthesis. We're gonna move on to this one, and we're gonna apply the Morgan on this S, the Morgan for N. So S plus P naught R or Q. And then we're gonna put the Morgan sign here. And I'm also gonna write the name of the step, the Morgan for AND. Now I'm gonna do the Morgan for OR, and it's gonna be over here. So let's apply the Morgan for OR. So this is gonna be Q S naught, and oh yeah, I'm sorry about this, but I forgot to put this plus here when I applied the Morgan for N here. We're also supposed to apply the Morgan in this parenthesis here. So we're gonna have plus P plus S naught. And we're gonna move on to this part. And we're also gonna do the Morgan for OR here inside the parenthesis. But notice that we have two terms. And the only term that we're gonna do the Morgan for OR is the P naught and R. So this is gonna become P plus R naught, and then you have P plus R naught plus Q naught. And then lastly, we're gonna apply the Morgan for OR, and we're gonna end up with Q S naught or P or S naught, parenthesis closed, parenthesis S naught plus P plus R naught, and apply the Morgan. And apply, yeah, you apply the Morgan. So you're gonna have the parenthesis here still. Sorry. And then you have the Q naught. Close parenthesis. This is how you get your De Morgan form. And what they're asking for here is to simplify with De Morgan. And then we have to use a K-map to to check our conversion. So let's first simplify this equation because it's kind of messy here and it's going to be hard to draw a K-map based on that. So let's make sure we
So on the third line right there, when you take the knot of P naught R plus Q, wouldn't that be the P naught R, that all that gets knotted times Q naught instead of the it being a plus there, would it be a
Oh yeah, because yeah, you're right. I'm sorry about that. Yeah, so you're saying yeah, I see what you're saying. It's just gonna be multiplied by this Q naught, right? Is that what you said?
yeah.
Yeah, I'm sorry. Sorry about that. Yeah. Oh, I wrote it. I think I wrote yeah. The fourth line or the fifth line, the last this one. Is that what you meant?
Yeah.
Yeah. Sorry. But you're right. I made a mistake there. I'm sorry. But now we're gonna simplify that, right? Because we're trying to get this is, by the way, this is our G. This is our G naught because we apply the Morgan here. So to check with a K-map, you pretty much need our G and our G naught to make sure we have a full K-map with ones and zeros. So let's look at the equation again, and uh, let's do let's simplify the equation and then apply the Morgan here, just to make sure we got the right answer. G equals Q naught or S P naught R plus S. S and P naught R plus Q and then close parentheses. So first we simplified this by doing Q Q P naught R plus P naught R S plus plus, and then we multiply it here. P naught R S plus S Q, and we still have the Morgan sign. And now we also see that we have like terms here, so we can cancel one of them. And once you apply the Morgan, we get we get Q naught P R naught times P R naught S naught times S naught Q naught. Let me just double check. Oh, sorry, I'm sorry. You have to add these because we're applying the Morgan for OR. So we do Q. And on this step, I want to apply the Morgan for OR and N at the same time. So we can add these terms and multiply them. So we're pretty much changing from POS to SOP. So we're gonna get Q naught plus P plus R naught parenthesis times P plus R naught plus S naught parenthesis S naught plus Q naught, and that's our G or G prime. So let's find the K maps for this one. So let's draw K map. So 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. We have A, B, C, D. So I want to start by this S naught and Q. This pretty much means 1 and 0. If you guys remember, when we have max terms, we have to simplify, or we have to modify, we have to invert them because we're trying to find our zeros, not our ones. So whatever this is telling me, I'm gonna invert that. So that's why my S naught, we're calling it a 1, and my Q, we're calling it a 0. So oh yeah, and so let's find what that is. I'm too used to the A, B's, and C and D. But let me write this as P, Q, R, S. So let's find where S naughts are. So we have, or pretty much 1, because S naught is going to be a 1 here. So our S, we have S being 1 here, this part, which is going to be our zeros because we're finding max term. So we're going to write it as a 0. And it's also a 1. It's also a 1 here. And then our Q is going to be 0. So our Q is 0 here. We already put it there. And it's also 0. Also 0 here. And here. Just double check. Wait. 0. PQRS. I'm not sure. I'm sorry? A Q naught on the end? Oh, this is a Q naught? Oh yeah, I'm sorry. That's why it's not working. I'm sorry. Thank you, appreciate it. So we have a 1 and a 1 here because it's S naught Q naught. So because we know that it's going to be a 1 here and here, so 0, 0. Now we're going to look at P or R naught or S naught, and that's a 0, a 1, and a 1. P is 0, the first line and second line. So, and then our R naught and S naught, they should be 1s, and they're 1s in these two lines. And since P is our variable that's changing, and P has to be 0, we're gonna put a 0 on these two lines. And that's how we check this part. And now we're gonna check the Q naught and P and R naught. And that's just gonna be, we look at, should be 1, 0, 1, and that's gonna be right here. So if you try to plug it in your equation for your G, you're gonna find your values of 1. I'm sorry this is confusing. Do you guys have questions? Okay, I'll move on to the next one. This is they give you a K-maps, and you have to find a literal canonical sums of minterms. Literal means we're trying to find the version of the letters, right? So A, B, C, not numbers. So what we're gonna do to find them, we're gonna find minterms by pairing ones. We have a pair of 4, and we have one pair here, and we can also do this one. So we have to find the equation for this now. So let's start with A right here. A equals, so it's F equals, we have A naught, B naught, and the variable that's not changing, it's C. So it should be A naught, B naught, and C plus, that's our first pair. And then let's find the big pair of 4. So we can see here that the variable in AB that's changing is the A variable, and our B variable is staying the same. So this should be B. And then for the CD part, we see that the variable that's changing, it's D. So this is gonna be, so you see that this is, the 0 remains 0. So this is gonna be C naught. And then we have to find these other 2 pairs. So let's find this one first. This pair will be, let's look at AB first. For AB, they stay the same, so it should be AB. And let's look at the variable that's changing for CD. The variable that's changing for CD is C, because C is going from 0 to 1. So we're going to keep our D. And our answer is ABD. Lastly, we have our last part of the equation. And it's, oh, I'm sorry, you have a question? Or you got it? Oh. So lastly, we're gonna look at this bottom pair, and we have A, B naught, because that's not changing. And then we look at our CD variables over here, and we see that our C stays, our C is changing, and our D stays the same. So this should be A, B naught, C, A, B naught, or sorry, I'm sorry. A, B naught, D naught. Let me just double check I did this right. So A, B naught, and then C changes and D does not change, and D is D naught. So this should be our equation for our literal canonical sum of minterms. B, let me just check on time, everything good. And then let's go to, oh, I'm sorry guys. This is the minimized SOP equation. This is the minimized SOP equation. In this question, they're asking for the literal canonical sum of minterms. So they're asking for every single every single one that you have here. I apologize for that. So instead of like finding this would be normally what you write for if you're looking for your minimized SOP. That's the equation you give them. But in this case, they want the full equation where we're not combining terms and we're just listing the terms by each one at a time. So let me just rename this. This is D or E. For A, they want us to write it like this. So the first, and you, since it's minterms, I like to write the sigma, and you do, let's look at the first one we have. A naught, B naught, A naught, B naught, C. And remember guys, this is 0, 1, 3, 2. So whenever you're looking at these, you don't look at this third one first. The one that should come in first is this number 2, because if you think about it, if you have 0, 0, 1, 1 and 0, 0, 1, 0, your 0, 0, 1, 1, 0 will come first because that's 2 and the other one is 3. So make sure you think you think about this, because if you write it in the wrong order, it's still right, but your professor could take points off of that, because it depends on your professor if they're strict or not. So make sure you do this the right order. I just want to mention that the same applies here into this part, because this is the 1, 1. So when we're gonna look at each row, we're gonna look at this row first, this row second, and we're gonna skip this row because this is the row with the 1 1s. And we're gonna go to the fourth row, and then we go back to the third row because that's the order. So let's move on to so let's finish this. And we have A naught, B naught, C, D naught. And then plus, let's look at our third one. This is A naught, B naught, C, D. Do you guys see where I'm getting that from? Okay. And we go to, this is A naught, B, and then C naught, D naught, plus A naught, B, C naught, D, plus, now we're gonna skip the third row and we're gonna go, let me just skip and go to this one, and we have a 1 here. And let's see, that's A, B naught, C naught, D naught. And then we have one more in this row, which is A, B naught, C, D naught. And then we're gonna go back to the third row, and we're gonna have A, B, C naught, D naught, plus A, B, C naught, D. And then lastly, this will be A, B, C, D. Does that make sense? I just wanna, in the interest of time, I don't want to work through all of these because I have more to show to you guys. But for the I just want to run through these. So for the compact canonical sum of minterms, you would just list the numbers, which in this case it'd be 2. This is 2, 3, 4, 5. Then we skip the third row. This is 7 or 7, 8. Go to 9, 10. We're not counting this, and you're not counting this. Let me just write it down. So if you don't want to write it like this, you would just write it as 2. I mean, if they ask for literal, you write it like the way I showed you guys. If they ask for a compact canonical sum of minterms, you're gonna write it like this. So 2, 3, 4, 5. We're gonna skip the third row. We're gonna 6, 7, 8. Because we're just going in numerical order. So this is 0, 1, 2, or 0, 1, 2, 3, 4, 5. And then we go back here and it's 6, 7, 8, 9, 10. This is 10. And then we go back to the third row and finish on 11. So this is 12, 13, and 15. This is 14 and this is 15. Does that make sense? And if you guys want to do that for the max terms, this time you would do the same thing but with zeros. Now but keep that in mind for max terms. Whatever you get for the 0, for example, this is a 0, and the way you describe it, it's not A naught, B naught, C naught, D naught. You're gonna flip them. The same concept that we worked out over here in the De Morgan. So this will actually be A plus B plus C plus D, all in parentheses, if you were to write it. And then you would move to the next one and do A plus B plus C plus D naught. See that I flipped whenever I had a 1, it's a 0. Whenever I have a 0, it's a 1. And you would go through each one of these, and that's how you get your literal. And if you wanted your compact, it's even simpler because it just be 0, 1, and then you'd go 2, 3, 4, 5, 6, 7, and then you skip the third row, you go to the last one, 9, 8, 9, 11, and this is 14. So same concept, and yeah, the circuit, I'm pretty sure I wrote the minimize SOP equation. To write the circuit, you would just uh, make a circuit out of this equation, which would pretty much be writing these three into an AND, and you OR it with all of them, and you pretty much write these into an AND, these into an AND, these into an AND, and at the end you OR all of them. Would you guys want me to draw the circuit, or can I move on to the Unit 2 content? Can I move on? Okay. And truth table time diagram, I assume you guys are pretty confident with it? Okay. And here are the slides for muxes and decoders and encoders, just for you guys to look as a reference. And here are more slides. I'll just give them in the interest of time and just work on the problems. If you guys want to look at them, the slides are in the Discord, so you guys can just take a look at it. Just want to point out for this one, they might give you a question similar to this on the test, where you have to like kind of describe which one of the memories are like cheaper, or like how fast they are. So make sure you know like the characteristics of each and single data memory. So we usually split it in RAM and ROM, but make sure you know like flash, you know EEPROM, you know EETPROM, because they have differences and you might need to know how to like explain them as a multiple choice. So make sure you guys could go back to this slide and read it. Register files, here's the slides. RAM, we have more information more information in ROM, and more information on to find the type. And let's go work a problem with the types. So we have to match each one of these and match it with its appropriate memory type. Let's start with the first one. A vehicle unit contains a memory with unique security code that cannot be changed. Your vehicle's audio unit code should be in your owner's manual. So the key message, or the key word here, is unique security code. From there, we know it's reprogrammable, and because it says security code that cannot be changed, we know it's not reprogrammable, and that leaves us with two options. Is it mass produced, or is it the OT-PROM? And since this is a specific it's a specific code, each car has its own unique code. We know that it has to be OT-PROM because it's not being mass produced. It's each car gets its own code, so it has to be OT-PROM. And now let's move to the next one. A digital frame holds up to 32 photos, which can be uploaded by the user and changed at any time. The frame displays different photo every minute. This one is kind of tricky because it doesn't give you much information. You don't know if it's volatile or non-volatile, if it has power or if it doesn't. So you kind of have to, if you're not sure about this one, you could go back to it. But we can also see a couple of things here. It says it holds up to 32 photos. That's not a lot, but that's not like it's a good amount, I'd say. So it doesn't tell us much, but it says that it can be changed at any time, and it displays a different photo every minute, which is considerably fast compared to most of the data memories here. So I want to say this is a non-volatile, and I would look at the options we have for them. We have, it could be non-reprogrammable, or it could be programmable. And we know it's programmable because you can change it, the user can change it at any time. So we rule out the non-reprogrammable options. And to see which one of these programmable options we have, which one's going to be the answer, we have to remember at the definition of all of these. So EEPROM, they're gonna mention that it's something old or something from the 1980s, and we don't see that here, so we can rule out that one. Uh, EEPROM, they usually tell you that oh, this has to be changed one at a time and not can be changed at any time. And then from that, the only reasonable option that I see here is Flash, so we're gonna go with Flash. Does that make sense? So we kind of have to go by eliminating it and making like sense, like which one fits better. And this one is a car radio can be programmed to select the driver's favorite stations, but the programming is lost if the battery dies. So this one, I think it's pretty easy because it tells us that it's a volatile memory. So we know it has to be either SRAM, DRAM, or register file. And normally for register files, they usually will tell you, uh, they will give you more information about it because we know that register files can write and read at the same time. And in this case, it doesn't tell us much. It just tells us that it programs the driver's favorite stations. So I want to rule out the register file option. And now we have to look at SRAM and DRAM. We know that SRAM can store less data than DRAM, and uh, a car programming favorite driver stations. I don't think that's a lot. Like if you think about it, and you could also look at your other options down the road here. We'll see that there's another one that will fit DRAM more. So I want to call this SRAM just by elimination. And I'm actually gonna move on to the one that's the DRAM. Sorry for the spoiler, but this one is a video gamer relies on type of memory to maintain the current picture in her video game while she's playing. So this one requires a lot of memory and data to maintain all of it, which makes me think that this is gonna be DRAM because it can store more data. And by knowing this one, you have to assume that this can only be SRAM because we already used DRAM. Sometimes this is how I work these problems out because they don't give you all the information you would need. Like they're not gonna tell you, oh, it doesn't hold much, it doesn't hold a lot of data. So you kind of have to go by elimination. And we can tell that a video gamer that relies on this type of memory to maintain the current picture will take more data, more storage than a driver favorite station. And now we're gonna go back to this one. When a popular children's doll hand is squeezed, she repeats one of the three pre-recorded messages. So for this one, we can already tell that it's non-volatile because there's no power. It doesn't need power to work. So because the doll is working without power, you can like it'll repeat the pre-recorded messages and it's not connected to anything. So we can say that it's non-volatile. And the question now is is it non-reprogrammable or programmable? And we can see that it has to be non-reprogrammable because she will repeat one of the three pre-recorded messages. So it's not like you can change it whenever you want to. So you have to assume it's non-reprogrammable. And the only option we have here is mask, but it makes sense too because they're gonna produce a bunch of these dolls and sell it in the market. So this fits the mask option. Um, let's go now to a portable device stores the names of the of active club members. Names may be individually added or removed using buttons on the device. So for this one, I think this part is the key here. It says names may be individually added or removed using buttons on the device. So as I mentioned before, EEPROM, you can only change one bit at a time. And because of that, this we can associate it this type this situation with the EEPROM. Does that make sense? You kind of have to look for keywords on this one. Keywords will always like show you what the answer is. And let's move to the next one. Used by an engineering student in the 1980s to develop microprocessor programs for a class. The student likes the fact that he can reprogram the chip but doesn't need a battery backup to maintain the program. So we know this one is non-reprogrammable, or I mean non-volatile, because it doesn't need a battery to back up the the program, or yeah, to back maintain the program. And we also see this keyword here, 1980s. So we can tell that it's gonna be EEPROM, because whenever they mention the 1980s, it's gonna most likely be the EEPROM. And lastly, we have a small memory truck. And the truck holds data sent to it from sensors under the vehicle's hood while the truck engine is running. The vehicle occupants can dial through the data to check current readings of mileage, exterior temperature, and estimated miles remaining on the current tank of gas. So we can see here that it's sending data. It's sent data from the sensors, and it's always uh, checking data through current readings. We see it's doing multiple things. It's writing and reading. This one, I think it's pretty obvious. It's a register file. So for register file, it's usually gonna read something from from whatever you're doing, and it's gonna write. It's gonna be acting on something. And that's how we did this question. Do we have any questions on any of these memory types? How to explain them better or something? Okay. So this is also on the slides. You guys can check it out. And I want to work a problem of decimal conversion. So 8.75. The way I like to do this is, all right, blinks. So let's start with 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of -1, 2 to the power of -2, 2 to the power of -3. And I think that's good enough. So let's first start with the simple one. 8 is just 2 to the power of 3. So we have 1, 0, 0, and sorry, I missed the 2 to the power of 0. 2 to the power of 0, 2 to the power of 1, -1, 2 to the power of -2. That's all we're going to need for this one. And it's going to be 0. And let's think about 0.75. We have 0.75. 2 to the power of -1 is just a half, right? So a half is 0.5. So the way you do this, you look at this number, and you're gonna check if 2 to the power of 1 or 2 to the power of -2 can be subtracted from it. And you're gonna do that for every single component until you can subtract -0.75 and get it to 0. So what I'm saying is we're gonna look at 2 to the power of -1, and we're gonna do 0.75 subtracted by it. Once you do that, you get 0.25. Because you were able to subtract it, you're gonna put a 1 for the 2 to the power of -1. Now 2 to the power of -2, that's just 1/4, which is also 0.25. So we get this 2.5 that was remaining here. and we're gonna subtract it. We're gonna subtract it by 0.25. That's gonna give us 0. So we're gonna put in a 0 here, and 8.75 in binary is simply 1, or I'm sorry, 1, yeah, 1000.11. That's how you write 8.75 in binary with a fractional conversion. Let's move on to a more difficult one. Is it okay if I erase the word? Let's go to a more difficult one. So same way, we have 2 to the power of 1, 2 to the power of 0, 2 to the power of -1, 2 to the power of -2, 2 to the power of -3, and let's do one more, 2 to the power of -4. So we know that 2 is 2 to the power of 1, so 1, 0, point. And let's think about 0.375. 0.375. Can we subtract 2 to the power of -1, which is 0.5, from 0.375 and get a positive number? No, so we're going to put a 0 here because you can't subtract it. Now 2 to the power of -2, which is 0.25, as we said before. Yes, we can subtract it here. So let's subtract it. We got 5, we got 2, and we got 1. So because we're able to do that subtraction, we're gonna put a 1 to the 2 to the power of -2. And let's think about what 2 to the power of -3 is. It's 1 over 8, which is 0.125. And if we get this the remaining subtraction here, and we do 0.125 minus 0.125, that's going to give us 0, and we put a 1 for 2 to the -3. And we get our answer, which is 10.011. Does that make sense? Do we have questions about this one? Okay, let's do the last binary one. We have 5.1875, and this is 2 to the power of 1, or 2 to the power of 2, 2 to the power of 1, 2 to the power of 0, 2 to the power of -1, 2 to the power of -2, 2 to the power of -3, 2 to the power of -4. So for 5 is simply 2 to the power of 2, which is 4. That's a 0. That's a 1, because 4 plus 1 equals to 5. So we found the binary part. That's pretty simple, or the whole number part. Now we have to find the decimal part again, and let's look at 0.1875. 0.1875. 2 to the power of -1, that's 0.5. We're not going to be able to subtract it. 2 to the power of -2, that's 0.25, and we're also not going to be able to subtract it. So let's look at 2 to the power of -3. That equals to 0.125. 0.125, right? So we're gonna, this one we're able to subtract it. Let me just put zeros here since we're not able to subtract it. And once we subtract it here, we get 5, 2, 6, 0. That's what we have. So we're gonna put a 1 here. We still have a remaining number here, and we're gonna take a look at what 2 to the power of -4 is, and 2 to the power of -4 is 1 over 16, which is 0.0625. So if you do 0.0625 minus 0.0625, that's 0, and you have a 1 here. So your final answer for 5.1875 will be 101.0011. Does that make sense? Okay. let's move on to the next part, is binary arithmetic. And this is the problem that we're gonna work on now. It's BCD. And for BCD, what I like to do, I like to look at this number first, the X that they give you and the Y they give you. We have 7, 4, 9, 6. And that's plus 4, 3, 5, 8. If you do that in your calculator, you're gonna get, let me just check. Let me just do that real quick, because you are allowed calculators in the test. So 7,496 plus 4,358. This should be 11,854. So whenever we add these two numbers, it better give us that in binary. So let's start that now. So we have 7,0,1,1,1 plus 4. And the way we do this, we add each individual number if it's corresponding. So we're gonna add 7 plus 4, which is 0,11 plus 0,100, and now we're gonna go 4 and 3, and then 4 is 0,100 plus 3, 0,011, and we have 9 and 5. So 9 is 1,001, and 5 is 0,101, and we have 6 and 8, 1,000. So let's start from right to left. Oh, sorry. Let's go from right to left. And what we get here is 0 plus 0, 0, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1. Does that give us 8? No, it does not. So here's the trick about this one. Since it did not give us 8, you guys learned in class that if you don't get the answer that you're looking for, you just add 6, right? So we just add 6 to it. 0, 1, 1, 0. Now if we do the addition here, we get 0, and 1, we get 1. Move a 1 here, and we get a 0. Wait, let me double check. This should give me an 8. Let me double check I didn't do anything wrong. Let me check. 0, 1, 1, 1. Then we add 0, 1, 1, 0. Okay, so that's a 0. Get a 0. 1 up. Does that have the number right here? 0, 1. 0, 0, 1, 1. 1 should be 0. Let me check if I added these right. 7, 7, 4, 96 plus 4, 3, 5, 8. Oh, I'm sorry. Yeah, whenever I added these numbers, I told you guys the wrong number. If you add 7,496 plus 4,358, you get 11,854. So this is correct. It makes more sense now. Sorry about that, guys. And we got 4 here. We have a 4 here, right? So that matches. We're good to go. And we have a carry here because we put a 0 here and we're gonna carry the 1. So let's add this one first, or let's add the 1 later, and let's do the addition here. You get a 0. 1 plus 1 is 0. 1, 1, 1, 1 plus 0, 0 plus 0, that's 1. We get 1 plus 0, that's 1. 1 plus 0, that's 1. And now we're going to use that carry. We're going to do 1 plus 0, that's 1. 1, 1, 1. We should get 5. We didn't get 5, which means we have to add 6, right? So we do 0, 1, 1, 0. 0 plus 1 is 1. 1 plus 1, 0, carry 1. 1 plus 1 plus 1 is 1. And carry. And we get 1 plus 1 is 0. So we get 5, right? 5 with a carry of 1. So this is starting to look like the answer we were looking for, and we're gonna at this next move on to this part. So if we do 0 plus 1, that's 1, 0 plus 1, that's 1, 0 plus 1, that's 1, and then 0 plus 0, that's 0. We have to add the 1 now, the carry that we had from before, and then 1 plus 1, that's 0, carry 1, 0, carry 1, 0, carry 1, 1. We should get 8, and we do. So we did this part right too. Let's do the last part, and this should give us 11. So 1 plus 0, 1, 1 plus 0, 1, and then 1 plus 1, that's 0, carry 1, and we have a 1. We have 2, or 1 plus 2 plus 8, that equals to 11. This is our answer. Yeah, so you guys can see that we got 11,854. In binary, we have 1011, 1000, 0101, and 0100. This is this is the answer, and we can check our work by just looking at the numerical decimal number. And seems like we're running out of time, so we're gonna have to stop here. But you can look at the other slides. If you guys have questions, just let me know. Just send me an email, or just send a message in Discord, and I'm gonna try to help you guys as much as I can on the Discord. Thank you everyone for coming. Appreciate it.